Good afternoon, everyone. Welcome to our workshop on Tsunami Inundation Database Portal. I think we have something really nice to show you today that for those that do tsunami work, I think you'll be excited by this new tool that's been developed. My name is Tom Shantz. I am formerly with Caltrans Division of Research, and now I'm kind of a semi-retired, a semi-lazy retiree. The agenda for today is I'm going to provide a brief overview of the program that really spawned the development of this web portal, and followed by that, Yusuf Bezorgnia will say a few words. Hopefully, a kudos to Sylvia for doing such a nice job on the web portal. We'll hear from Pat Lynette on some of the technical issues with the data, particularly bathymetry density issues, and when we can do data lookups and when we need to do the energy grade line method. And then Sylvia Mazzoni will present the web portal and take you through a detailed demonstration of its features. And then, quite important, we would like to at that point open up to discussions and get feedback on features you like and maybe things that you might have issues with. This project came out of what's called a Transportation Pooled Fund project. And this is when states get together and share or pool research monies on a common interest topic. And I'd like to credit the state of Oregon for being persistent with all of the West Coast Pacific Ocean bordering states and really press the need to develop a tsunami guideline that could be used for the design of bridges and really try to get everybody on the same page. And so that project started in 2015. And recently was completed. You can learn all you want about the project at pooledfund.org. And then if you search the 5307 number, all that information will come up. The final report is complete and it is posted there as well. And it provides a lot of the technical discussion of some of the issues that you're going to hear about today. And my hope is that we will also post a link to the final report from the web portal website as well. The objective of the Pooled Fund project really had three components. The first and most relevant to today is the characterization of tsunami hazard at 1,000-year hazard level. That hazard level is different than what had been done in previous work, in work done by ASCE, which is typically done on the 2475 hazard level. But since all of the DOTs do our seismic hazard at 1,000 years, we felt for tsunami hazard, it should be at 1,000 years as well. So that's how we ended up there. Other components of the project less relevant to today is how do you take the hazard values of wave height and velocity or some combination of those and turn those through some simplified procedure into loading on bridges. And then writing that all up into a guide spec, which ultimately the goal is to turn that into an AASHTO guide spec. This was a rather ambitious project, and Oregon was the lead state. They managed the project and they contracted with Peer. And Peer assembled the team that you see on the right, and there were many other contributors, including FHWA and representatives from all the states. But the main two folks I want to call out here are Hong Ki Theo, who's with AECOM, who did the tsunami hazard, and Pat Lynette at USC, who was the project manager and did lots of uncertainty characterization in our modeling, particularly with the propagation of waves inland, comparing model results to those observed in Tohoku, for example. When this project got started, the hazard data for California was largely complete from earlier efforts. But that wasn't true in the other four partnering states. And so In this project, much of the effort then was to develop that data. Oregon decided that they were going to contribute additional funds and develop data at a higher bathymetric density of 10 meters, whereas most states, we only had data at 60 meters. And that's an issue that will be addressed in a minute by Pat. So I did want to call out the data that we use, particularly for California, had a long history in that those kinds of studies started with evaluation of Diablo Canyon, and then they extended up to a couple of peer projects, and then CGS kind of contributed and did a lot of modeling of the Cascadia subduction zone. So there's been many iterations with this, and a lot of eyeballs have been on the work that Hong Ki has done. So as we were nearing completion of this project and we were starting to turn around and provide data for end users, it became quite clear that we needed better tools to help engineers on the design floor. One might think that particularly in states like California and Oregon, where we have the denser tsunami data, that it's really just a lookup exercise. And so, hey, you know, why not just look it up in data tables, pull out the numbers, you're good to go. And the fact of the matter is that it really is more complicated than that, because a lot of topographic features are smaller than that 10-meter grid density. And so you really find yourself having to look up at a large number of points and looking at those relative to satellite images. And so without any tools, that can be a rather laborious process. We felt that there is good opportunity to streamline that. And then finally, very few engineers really know how to do the energy grade line method. And we felt to the extent that we could ease that burden would be quite welcome as well. So at that point, Caltrans turned to UCLA and the NHR3 program to develop a web portal that could take on these tasks. And then today is really the first public unveiling of that web portal. So we're excited for everybody to see it. So with that, I'll turn it over to Yusuf then.
Very good. Thank you very much, everyone. I appreciate that. So I really want to thank and give credit to the people that really they worked very hard, especially to Tom, Pat, and Sylvia. They spent tremendous amount of time in the last several months, especially Sylvia, and they had numerous conference calls, many conference calls. Few of them I attended, only few of them. So really, that was a major effort by all of them, especially Sylvia. She did really a great job. Obviously, we couldn't do it without financial support. Caltrans, obviously, as always, since 20 years ago, Caltrans has been supporter of many interesting and applied research projects. PG&E was contributing, and also NHR3. We really appreciate all the sponsors. Finally, I really like to thank all of you. 30, 40 people already registered, 50 people registered, 35 people already online. I really thank you for attending the workshop. Appreciate that, and I'll pass it to Sylvia.
I just want to make the introduction that the hard work in this project really comes from Pat. My job was just to do the user interface, so that the technical details that Pat is going to go into are really the most important core aspect of this project.
Thank you, Sylvia. I think you're underestimating how much time you put in, but I'll take it. All right, so I'm going to focus here on the hazard assessment part of that bridge project that Tom and Yusuf introduced. And so, again, I want to iterate that the tool that Sylvia put together and all of the tsunami hazard that we're going to introduce here, it was really made for use with this bridge guide spec. And so for sure there will be other uses for this portal that Sylvia put together, but at least, you know, what we're really going to focus on today is the data that was made for the bridge project and how to use that hazard data within this bridge guide spec project. And so Tom introduced the group. So what I'm going to talk about is the hazard. So it was primarily me and Han Ki. And so it was our job to come up with flow parameters to then pass off to the structural loading group, which was Michael Scott at OSU, Ian and Dennis, who I think are both on this call. They really pushed through the loading specs quite a bit in probably the last 2/3 of the project. And then Tom and Jerry, and then Tom Murphy really wrote the guide spec, put it all together. Hazard and mapping overview. So what did we do? So we created a tsunami hazard map database, and these maps are at the 1,000-year hazard level, really 975. There are going to be two major classes of inundation modeling. One set of results at the 10-meter resolution, so this is horizontal spacing at 10 meters, and another group at 60-meter resolution. The other main pieces of this hazard and mapping project and the effort was the quantification and inclusion of uncertainties, and so that made its way kind of indirectly into the method that we came up with, coming up with the flow depth and the flow speed. And then that last part, which is really the important piece, is the specification to provide the hydro information that is site-specific to the bridge project. There are two main options inside this bridge guide spec. Level 1, which requires you to go to the energy grade line analysis, which I'll introduce and talk about kind of quickly. And then level 2, which is kind of that refined site-specific modeling where you are doing 10 meters or less resolution modeling for your particular area of interest. And so a lot of California and Oregon already have 10-meter mapping results for this project. So they are automatically in this level 2 analysis. But in other places where it's only 60 meters, the user or the engineer, if they wanted to have site-specific high-resolution modeling, they would need to go and do it on their own. Talk more about that. So first, where do we get the tsunami hazard from? What's our starting point? So it's all probabilistic. And again, this was done by Han Ki. This starts with a unit source database across all of the subduction zones in the Pacific. And so these are relatively small sources. You put essentially a block of energy in there and you propagate it out with your tsunami equations. You do that for thousands and thousands of unit sources. You're making the assumption that you can linearly superimpose all these different unit sources together. And so what it allows you to do is it allows you to kind of create any arbitrary initial tsunami condition that you want with linear superposition of all these unit sources. So you can look at any potential earthquake generated tsunami that you want. And so that's really what Han Ki does. He just generates thousands and thousands of scenarios with this unit source database, and he aggregates that hazard along the 100-meter depth contour offshore of all of the Pacific states. And so then what you're left with that aggregated hazard is a hazard curve. And that hazard curve is tsunami height versus frequency of occurrence, or you can think of it as a mean return period. And so from that hazard curve, you can pick out a tsunami amplitude, which corresponds to the 1,000-year, the 500-year, the 2,500-year. You can get all your probabilistic hazard from that offshore hazard curve. But that is important to note that that full probabilistic study kind of ends at the 100-meter contour. And then what we do, and I'll talk about this in a bit, we're going to take characteristic sources near our hazard level of interest, and then we're going to run a set of inundation models to give us the inundation hazard. So it is kind of a two-step process, the way that Han Ki does it, and that's done entirely for computational reasons because it's just too much modeling effort to do a full inundation probabilistic analysis, at least right now it is. All right, so then what you're left with, again, this is an example. This is that 1,000-year tsunami amplitude along the 100-meter contour. So this is the main result. This is the main starting point for the bridge project. And so you can see how that amplitude varies depending on where you are. Along the 3 western coast states, you see that tsunami amplitude is largest from Northern California through Washington. All right, and so then with that offshore hazard information, like I said, we're going to select a set of earthquake scenarios which match the offshore tsunami hazard that we're targeting. So we're going to look at that 975 offshore hazard amplitude, and we're going to pick a set of earthquake scenarios that are close to that offshore tsunami amplitude. And then we're going to run it with our traditional tsunami models with nested gridding to some level of refinement for inundation. What you're seeing is the grid coverage for our 5 Pacific states. The blue boxes represent areas where you have 10-meter resolution modeling, and the red boxes represent areas where you have 60-meter inundation modeling. And so what you'll see is that in California, essentially where there's people, where there's development, we have 10-meter coverage. There are some gaps in there, but we have 10-meter coverage in the vast majority of areas of interest. Along the Oregon coast, it's a similar configuration there. There are more gaps filled in with the 60-meter modeling there on the Oregon coast. And then what you'll see in Washington, Alaska, and Hawaii is just 60-meter modeling in the areas of interest. That inundation results for all these different grids is going to look something like this. So this is just an example of this flow depth. So it gives you the flow depth at the 975 level for this particular area. From the modeling, we have these maps of flow depth, we have maps of flow speed, we have maps of something called momentum flux, which is useful for figuring out drag forces on buildings. All of these surfaces are included in the tool that Sylvia is going to introduce. That's where the hazard comes from. And so how are we going to use this hazard to get to a site-specific analysis? Okay, so when Sylvia shows the portal, it's going to look a whole lot prettier than this, but this is the general layout, right? So there's going to be a red line, which indicates what the shoreline location is pre-tsunami. So this is mean high water shoreline position. That's the red line. The black line that you'll see is the inundation limit. That's how far the 975-year tsunami goes inland. All right. And so then what you're going to do is you're going to, for the level 1 analysis, you're going to create transects. All right, we'll talk about that in a minute. But this is the basic set of data that you're going to see. And then you'll also see more information that Sylvia is going to talk about. But this is it, right? You have a shoreline contour, you have an inundation limit contour. Your site is probably going to be in between those two. When you're talking about a level 1 analysis, so a level 1 analysis is where you only have the coarse resolution inundation results. So for this project, it means you're going to have the 60-meter grids only. You don't have 10-meter grids. And the reason that we fall back on this energy grade line analysis for the coarse resolution modeling is because we don't trust particularly the velocity predictions from the coarse resolution modeling. It's just too rough, and the models that we have right now, there's a lot of imprecision and quite a bit of inaccuracy in velocities, and we just don't trust it with the coarse resolution. As you get to finer resolutions, it starts to converge and it starts to look much better, but we don't trust it for the coarse. And so as I go through this, what you'll see is that, yeah, I mean, we don't trust that 60-meter velocity, but we don't trust the energy grade line analysis a whole lot either, right? So there's kind of this balance here between, well, which one is better, or if you look at it from the pessimistic side, which one is worse? And just from using it and trying to understand the variability and the uncertainty, what we converge to is this approach, where for level 1, where you have the coarse resolution modeling, we have more confidence in the predictions that come out of the energy grade line analysis as compared to the coarse resolution modeling. Okay, so the energy grade line method was primarily developed for ASC 7. So the chapter 6 in ASC 716, which deals with determining tsunami loads on structures. Dave Kriebel was the original developer of this, and myself and a number of others who were part of that tsunami subcommittee contributed to it. It's essentially, conceptually, it tracks the total energy over changing ground elevation with energy dissipation due to friction. And it's a simple conservation statement which says that the change in energy in space is driven by the slope of the ground, and a friction slope. And that's really what it is. It's fundamentally quite simple. It's kind of a stretch to think that it should be entirely valid for a transient wave problem like tsunami. But a tsunami is long enough in some aspects that it's reasonable. And so the way that it works conceptually is you first have to create a ground transect. Along that transect, you have to find the location of inundation. And then you work from that inundation limit back to the shoreline, solving this energy conservation equation to figure out how high the water is and how fast it's moving. The only way that you can figure out that partition between total energy and kinetic energy is by specifying a priori a Froude number distribution. And so this is where kind of the magic behind the curtain is, and this is why the energy grade line works, is because you specify this Froude number distribution, which is really just a 1/2 power shape going from a maximum Froude number at the shoreline, which is either 1 or 1.2, depending on the property of the wave. For this project, we assume that it's 1. And it just decreases by 1/2 with distance power. So that's really it. You find that it can give you reasonable results, but there's an awful lot of scatter in the energy grade line analysis when you compare it to high resolution modeling. So for this project, the way it works is, so this isn't a great animation, but the way it works, you're going to create 4 transects for this bridge project. Whenever you do a bridge analysis, you have to create 4 transects. The first one is called a riverine transect, where you as the user decide what the expected dominant flow path will be from offshore to your location. It's called a riverine transect. And the reason we have this riverine transect is because most of our bridges tend to lie over channels, which we expect to be preferential pathways. We wanted to try to capture that effect of preferential flow pathway and bathymetry topography for the bridges. Once you have that riverine transect, you create 3 more straight line transects. You create a shore normal transect, and then 2 other straight line transects at +10 degrees and -10 degrees. So this is the straight line transect approach is similar to what is done with ASC 7, except our angle is more narrow. And we just found that that was more reasonable for the types of locations that we deal with bridges, which are often maybe a little bit farther inland than some of the structures that get dealt with in Chapter 6 and ASC 7. All right, so you have 4 transects. How do you deal with the 4 transects? So first, this is kind of the summary slide here. If the site location is in an area with 10-meter resolution modeling, the flow depth and flow speed from the modeling will be used directly for the bridge loading calculations. You're done. You don't have to worry about energy grade line analysis. So this is the great benefit of having high resolution mapping in your state, is that you can take the energy grade line method and put it aside or put it in the trash, whatever your preference of that is, right? So you can forget about it. You just pull the data point out of the database and you're done. On the other hand, if you're in a location that doesn't have the high resolution modeling, you need this energy grade line analysis for site-specific flow. So we create 4 transects. 1 is riverine and 3 straight line, a shore normal, and ±10 degrees. And so this last bullet is what we converged on for using the energy grade line method in kind of a stable way. So the design values are taking as the average of the middle 2 of those 4 transects. So what that means is that if you have 4 transects, and these 4 numbers, 2, 6, 7, and 8, are the flow depths given to you by the 4 transects. And these 4 numbers are the flow speeds as given to you by the 4 transects. Your design flow depth and flow speed would be the average of the middle 2. Those middle 2 do not have to come from the same transect. Essentially, we look at those 2 sets as they're independent. You just take the middle 2. And so this is in no way what we would call a statistically robust approach, but it's better than choosing one, or it's better than choosing the max. We just found from our tests of a lot of potential and existing bridge locations that this method of throwing out the high outlier and the low outlier and averaging the middle two gave us a number that tended to converge close to what the high resolution modeling would give. And so that's why we use this middle two approach. So when Sylvia talks about this section that gives you the design values, when you use the energy grade line method, this is where the design values come from. If you're in a high resolution modeling location, you don't got to worry about this at all. But when you're energy grade line, this is where your values come from. And so then once you have the flow depth and flow speed, you can proceed with the bridge loading calcs. You have various load cases that combine those two, flow depth and flow speed, and you can figure out what your loads are. Here are the two main links that exist right now to get all that information. I think Nick may have already thrown one of these in the chat. So the full report can be found at this first link. And then if you want a little bit more background and a little bit of a news story type write-up, you can see the details of the project here at this peer website. So that is all for the hazard. That's where it comes from. I guess I'll pass it over to Sylvia, and if you have any questions about how we do these things or why we do these things, we'll take care of them at the end.
Thank you, Pat. Well, my job was to take all the work that everyone has done before me and make it accessible to the public and also make it robust. I mean, we did have many meetings at the end. It wasn't about the technical computations, but it was really how can we make a portal that is robust enough for users to come in and be confident in how they're using it. So my job here is to right now just give you step-by-step instructions on how to use the portal. So I've given here a QR code. If you want to point your phone to that, that will give you access to the website directly. Of course, it's where you register for the workshop. But the goal here was to develop a portal. And as I said, I'm giving you the instructions to develop a portal that is intuitive and robust and be as fast as possible. So you access the portal, and as usual, you need to log in. This is a one-step. You do it the first time that you log in, and then you don't have to as long as you save in the memory. The important thing is we've taken everything into Amazon Web Services. The portal resides there. And so we're still working through all the in-between steps of setting up the email and things like that. So make sure you remember your password or set up a new account. If you forget it, or send me an email and I can reset it. But we should have this pretty soon. This is a public release, but you guys are the very first people to have access to this, and it'd be great if you take the opportunity soon to go to the website, test it out, and provide us the feedback so that we can always improve. So you log in the first time, and then as Pat has given you the instructions already, you can do two types of analyses. One is a simple database lookup. It's easy and pretty quick. And the simple input is just the lat and long. And then the second one is to do a database lookup plus the energy grade line analysis. It's an interactive process. And that's what I'm going to show you how to do these two steps. One thing to keep in mind is that the tool is computationally intensive. It does three different things in sequential order. First, it does the database lookup and interpolation. Then it needs to send the data to be transferred through the network to your local computer. And then your own computer needs to load up and show it on the browser. So you need to be a little bit patient because we can control the very first step one, but then the network and then your browser are in control of the second part of it, okay? So because, as it pointed out, it's a lot of data, just want to make sure that that's the most robust part is to be patient in visualizing the data. The best, we always like to put in, just sample values for the input format. And right now, I've set up a temporary password. In about a month, once I get the feedback from everybody, and maybe we could do some additional improvements, I'm going to remove that password. And the password is 1969. I'm going to show you where you put that in. So this is your little secret password. It's independent of your user password, okay? This is just in the very first screen that's going to be there. So as you log in, once you've logged in, you access the portal. Important to read the instructions. You only need to read them once. We've made this as intuitive as possible, but it's just good to know what it is that you're looking for. We've highlighted all the different steps that you need to do. And again, there's two different things that you're doing, either the database lookup or database lookup plus the energy grade line. And so the instructions just kind of give you a little bit more detail as to what to do. User input is pretty straightforward. So it's in the very first page. I always recommend to go ahead and start by clicking on load sample values, because that gives you the best format for your lat long. As you can see, it's integers, and you use a negative value for longitudes on this side of Greenwich. And so again, the sample values are given right here. So that's the very first step you do. Next step is you choose the overlay, because there's some nice graphics that we've overlaid. As Tom pointed out, it's good to visualize the surroundings of your data set. This is the computationally and network intensive and rendering intensive part of it. So maybe start off with a medium type of more than resolution. It's really the size of the data that's being displayed. And then if you want to start looking at pretty pictures, you can go to extra large, but then you'd have to wait a minute or so to get the data all loaded up. If you want to include, this is where the diverging comes in. If you want to include the energy grade line computations, you check this box. If you don't, you leave it unchecked. So I always recommend the first time around to leave it out, just to make sure that you're in a good location. Then this is right here is the temporary password. I put it outside of the box because we will be removing this step 4 eventually. And then all you have to do is press run. Once you've pressed run, as I said, you have to wait for processing. And this is something that we're all used to nowadays, since we spent so much time on the internet. I've put in this button here. It will show you, it will be grayed out, and it says processing, please wait. You can scroll up and down on the web page, but don't click any buttons, otherwise you're sending additional commands. And then also keep an eye on the little wheelie up at the top, because that's your browser. So the browser is going to end later than the computations are done by the computer. And that's dependent, again, as I said, on the network and your computer. So my recommendation in everything you do on the internet, always make sure that those two buttons release you, saying that they're done. And here's the results that come out when you do a database lookup. The database lookup is literally for your site, and this is the graphics, and I'll show you in the next slide also the numerical data. But it's kind of nice because it shows you where your site location is with respect to, here's the red line and the black line that I'll talk about, but Pat has already introduced before. And here's your site. It gives you information, the quantities at your site. You can choose whether you want to display the flow depth, flow elevation, flow velocity, momentum flux, the ground or seafloor level, or even just to remove the graphic. It will give you the values at your site, but as you hover over the figure, here of course not, it's a screenshot, it will actually give you local values. This is a medium resolution. It's not really about resolution because this is the resolution of the data, but just this is a medium size of the data set. And so it's very helpful because you can look at what your site is, location of your site, and additional information of what's around it, especially as you start planning if you need to do an energy grade line analysis. The data itself is right here. It's just below the map. So here's in this map case where I show a little bit more data set. Everything is given here. All the database values are given here. And the most important thing here is to look at what the program message gives you. If it gives you an okay, that means your data analysis is values that you have here are the values that are recommended. Sometimes if you're on the boundary, on the edges, the program will give you some additional information. And so this is pretty much the data that you get if you're doing a database lookup. Here's an example of the difference in the data that you're given, depending if you're going from small all the way to an extra large. Again, this was just something that we wanted to put into here just for fun, to give you the opportunity to see what's around the site and have a better understanding about the data that is shown. As you can see, the data is really only given in areas where there is data. It's outside of the inundation lines, there is no data. So this makes things a little bit faster, at least in the display and the data set. And what you can do is after the first time, if you want to visualize the data a little bit more, you can actually go back, reselect a different size and click run again, and you can do the analysis on your same site. As Pat already talked about, you'll see two different types of boundaries and additional data in your map. The shoreline boundary is shown in red and the run-up boundary is shown in black. You don't need it for the database lookup, but you'll need to know about it when you're doing the energy grade line. You can turn these on and off if you want to visualize them or not, but they're automatically on in your output. The additional data, which is what Pat has shown you, is an idea, just a visualization of the data regions. And so you can click on this button here on the top left, whether to hide it or show it, and then you can zoom out and kind of have an idea of where it is that you have data. As you can see here, this was the region that we're in, so there is more information in the selected region for your site. But it's just kind of good to give you an idea of what the different coverages are for the data. There is a little trick if you want to. You can zoom out, you can grab the pointer and move it to another place, and then double click on it again to run the analysis. It's an undocumented feature, and if you can get that to work, I recommend you play with it and get confident in it, because it's not as robust as I would have liked it to be based on user input. And then I wanted to highlight, as Pat pointed out, that you have different resolution in different regions. So if you look here in Alaska, the data is not as dense and high resolution as it was in the previous region, and same thing with Hawaii. What's interesting though is, and one thing I want to highlight is this, I use just a color array for the distribution of values here. And so if you have a small area, you may actually get more variation in colors and therefore better resolution in difference in colors than if you use a large area. Just because I've got 200 colors and then I do a linear interpolations of colors. So do not just go straight to an extra large data set, because it may not give you the detailed visualization that you want with a smaller data set. And so those are things to keep in mind that we included in the interface to give you a better visualization of the data that you're working with. If you want to do the energy grade line, or when you want to switch over to doing the energy grade line, I recommend clicking on the button that says Start New Project. And so that brings you back to the original input, and you go through exactly the same phase, except for that now here. So you've got the same coordinates, or update your coordinates. You can start with something small if you want. The most important thing is to check the box here to include the energy grade line computations. That leads you to a little bit more interesting interface that gives you a bit more options. Another set of instructions, more detailed instructions, you should read them, but we've included the instructions as you go through the process. And we've tried to make it as straightforward as possible. Just in numericals, you do step 1, 2, and 3. You define the riverine transect, then you define your straight transect, and then you run the EGL analysis. So it's pretty straightforward in the buttons that we've defined in the user interface. In defining the riverine transect, the first thing you do is you click the button that starts the interface, and then all you have to do is follow the directions. They're at the top of the plot and they're at the bottom of the map. They're the same instruction, just really depends on the size of your screen and where you're at. So follow the instructions. And so as soon as you start, it's going to tell you select offshore point. So something beyond the red boundary, which means something out here in the water. And so here it is an example. I've clicked a point. So as soon as you click a point, now it's going to ask you for points inside. It says select a location within the inundation zone. So that's between the red and the black boundaries, or select a site marker. So first you want to define the flow that gets you to the site. So you pick a number of points. So you follow exactly these directions. And to show here, that's what I have done in this example. I've picked a couple of points of where I assume that the water is going to be flowing. Once I've picked enough points, and the next point would be my site, you literally click on the site marker. And once you've done that, the instructions now change, and they tell you to select something not in the inundation zone, which is past the black boundary, which means somewhere out here in the dry land. And so that's what you do, is you click that last button. As you can see, Google Maps will show you the points and the lines that you have selected. And now you've done, you've defined your transect. If you want, you can clear it and redefine it, or you go to the next step, which is to define the straight transect. To define the straight transects, you only pick one point. And so that's what you do, is you follow the instructions. It tells you to pick a point beyond the red boundary, which is right here. So here's the blue point that I have chosen here. The program will automatically define these additional lines. Make sure that when you pick it far enough that the 3 lines do go into the water line, okay, outside of the shoreline. So just be really careful in doing that, but the program is pretty robust in finding those lines. It's really difficult to write an algorithm that is robust when we have coastlines that change in all directions. All you have to do is click this button, and now you define your straight transects, and then you can go on to run the EGL analysis. If you want, as I've mentioned, it's optional. You can redefine it, so you can clear them and redefine the straight line, the grid, either transects, and then you can go ahead and run the EGL analysis. As I've already said, be patient and wait, because there's significant computation and iterations that go through this process, as Pat already talked about as he explained what the process is. So just make sure that this button turns off and that your spinning wheel there is done. I could have added another layer of a spinning wheel there, but I think we're all kind of used to using the internet these days, that we're used to keeping an eye on these 2 markers. This is the data that comes out of this analysis now. You can see you're starting with the design values that we have from the database, but now there's even additional message here that the site is on the edge of the inundation zone, so with non-physical velocity, and the database velocity values should not be used. I leave that to you to interpret. Make sure that this is important. You have the technical background in using the data that is here. A lot of this you need to refer to the report and make sure that you're familiar with what is being output by the program. So here's your energy grade line output for the different transects. And we have plots of the data for the 4 different transect lines. So this is all visually here. It's interactive as can be. And then it pretty much becomes the iterative process of, if you want to select a new site or you want to redefine your transects, you can keep working until you get the results that you are looking for. Very important, feedback is key. In building this demonstration, I managed to crash the program. I believe it's because the data set, this is normal when you're working with this size of data sets. So make sure that you provide us the feedback, and you can always go back if you get a screen like this. Go back and send us a screenshot of the input. That's really going to help us to make the program that much more robust. I have here a tiny little video that I recorded a demonstration. So, and this is sped up 3 times just to show you that it's not just a bunch of screenshots. This is how you would get to the Tsunami portal. Read the description. There's even access to the peer project. We're going to be adding some more documentation on this website. Here you are, you enter it. Yeah, you want to make sure that you read the instructions and just step by step of how the input goes. So you put in your coordinates. You can update the coordinate values based on your actual site. And then you put in the secret password of 1969. And here you process and you wait. And as you can see, it loaded up relatively quickly. But again, this is sped up 3 times. So here's a visualization of the data. And as you can see, you can turn that off to see it, or you can hover near it to get what the values are near the site. You can then scroll down and look at the results, or you can even look at the graphics of the different quantities that are being displayed. And so that's pretty much what you have from the output. Then you can go back, and if you want, you can process it and visualize this in extra large. And here's a demonstration that it shows you how long it's taking, and I've sped up this 3 times. This is just the reality of the kind of data that we have. Maybe with enough use, we may go to some binary computations and things like that. But right now with this version, just be a little bit patient. But here it is right now, it's loading up the rendering, and that's really at my client side, not even on the server side. So here just gives you a little bit better view of what you have in your data set. It looks really cool, and it's kind of fun to see what the values are at your site or near your site. You can zoom out, as I showed you one of the screenshots, and have a view of the world. It was really neat to be able to, originally this was developed in MATLAB, and bringing this in, the vision that the team had and bringing this overlaying with Google Maps really makes it a lot better and more practical as a access to the data set. If you then switch over and go in and do an energy grade line analysis, you go pretty much through the same process as we had before, but now you follow steps 1, 2, and 3. So you read the step 0 is to read the instructions, and but it's very much a 3-step process. So you first define your river and transect. So you click the button to turn on the listener in Google Maps, pretty much. You pick your points, and in this interface, you pick one point on outside of the shoreline boundary, and then your site. And here it is. You've got the grid lines, the transects that you want. You can redefine them if you didn't like what you have picked. Here I picked something way off, but just to show you can do it. And then you click either the red button or the blue button. It's the same thing. They run the energy grade line analysis, but the blue button is the one you need to keep an eye on, as well as the spinny wheel on the top left here. See, it's moving a lot faster because this is 3 times video. And as you can see, it's doing a bit of computation, and it takes time. You can scroll up and down to visualize things, but just, again, please be patient with the program to render everything. And here it is. The rendering and the graphics is done, but then this is where you have the additional data. There's also a box at the bottom with optional input that just gives you the coordinates of the grid line. And that's pretty much it. That's the demonstration that we have in the instructions. We've given you the background to this. And it'd be great if you guys can go in and give us feedback. Again, there's always room for improvement and additional features that eventually we could try to add, and just really see the value in the work that we've put into it. So I think now I'm going to pass it back to Tom, or to pretty much to the audience if anybody has any specific questions. I haven't been able to watch the chat, but maybe I see that people have asked questions on this, so maybe Pat might want to start off with answering some of the questions that are from the chat. And thank you.
Thanks. It looks like Leslie and Kale asked about subsidence. So, Sylvia, I don't think we actually display the subsidence values anywhere in the portal. We do have them. They are being used. They're used to modify the transect value, the transect elevation when you're doing the EGL, and they could be displayed, I guess. I guess we just kind of forgot about that. But they are at the 975-year hazard, so they are consistent with this particular tsunami hazard. And yes, also different than the ASC 7 geobase subsidence, which is at 2475.
See, this is the feedback that we're looking for, is things that we may have taken for granted.
Yeah.
So,
yeah.
Any other questions?
Leslie, that subsidence information, it actually comes from the description of the earthquake sources that Honki generates. So those actually have the models of how the ground deforms upward and downward, and those are recorded, and an exceedance distribution is put on them, and that's how you get the 975 subsidence. What other questions do we have in here? Megan asks if the raw data can be accessible. I don't know what the answer to that is, to be honest with you. That may be at a higher project level to determine whether or not those raw data files can be given out. I don't know the answer to that. Yusuf, we may have to figure that one out.
Let's discuss it later to see how we are going to do that.
Yeah.
There is a question as to whether you can download this to, I lost that question, ArcGIS. It depends. I mean, the raw data, you would have to interpret it. And then what I've done is I've given you, let me see if I can it's in the video, but you can I do output the points, the locations of the transects. So if you want, you can bring those data over for the transects to ArcGIS or any sort of format that you have. We wanted to use Google Maps just because it's it's just easier to interface with. But the rest is literally raw data that you would have to interpolate or interpret for other programs. Any other questions? If anybody wants to speak up, you can unmute yourselves and ask questions if you like.
Hey, can I ask you a quick question here, Sylvia? Excellent. So this is fantastic work. You have taken something complicated and made it extraordinarily easy to implement. That must have taken a lot of back work. So I congratulate your team on that. You did a great job. The one question I did have was, how do you handle those places where you have overwash areas like a peninsula or something, right? Because in ASCE 7, they have like overwash points, but I don't remember how that's being handled with the energy grade line here.
Yeah, Sylvia, I can take that one. So Nick, it is not. Essentially, we did have some discussion about these sorts of situations a while ago. And the conclusion was that for the bridge type work, those situations are unique enough so that we didn't want to encourage the use of the energy grid line in those situations. So there are no overwash flow points like you have for things like barrier islands in ASC 7.
Any other questions or comments?
I have a question, Sylvia. Many times the delineation of the shoreline, just because of the challenge of doing interpolation with these data points, is that they'll want to make little loops instead of continuous lines, right? And you see that in some of the presentation. There's areas where you get the little red loops. When you implement energy grade line, if you actually have your transect go through a place to where you have kind of you're on the ocean side of that kind of loop shoreline, is it going to matter? Will it mess up your results if you choose a transect location that runs through those loops as opposed to something that's delineated as a continuous line?
So I'll let Pat answer this, but just on general terms, it's tricky, this grid line, the shoreline, as you can see here. Of course, it disappeared right when I want to talk about it. It's not, it's continuous, but then you've got loops, and that's why we're showing them as dots. And so the algorithm will actually go through. Pat, you wrote the core of the algorithm, so I'll leave you answer the technical part of it. But it's my understanding that it will actually compute through those areas.
Yeah, so this is actually a really nice layout of shoreline and inundation limit to give you an idea of the challenges that you can have here. And so you see that weird looking line that goes right through the river. And so that is because when NOAA created this particular DEM tile, they blended together different data sets, and there's just a wacky discontinuity of, I don't know what if you click on seafloor ground elevation, you can probably see it better, but there's a discontinuity at that line. And so in situations like this, if you were to the right of that line, you would probably need to be careful about how you applied the energy grade line method. And I might even venture to say that you might not want to use the energy grade line method in that sort of situation, because it's not clear in the raw bathy topo where the mean higher water shoreline should be in that river.
Okay.
Yeah.
I think this is my approach to this is, as we use this type of data and we make it more and more accessible, then the next iteration would be on improvements on the data and augmenting the data and the studies that we can do if we show value by making this data accessible. So it's that iterative process, right?
I have one other question too, if that's okay.
Mm-hmm.
Let me just say, Nick, this is a good example. There aren't a whole lot of places that look like this, but there are a few. Sylvia just picked a nice one.
It was one that showed all variations.
Yeah, all
No, it's good. You want to show it as bad as it can be, right? So everything else in reality will be a little better.
Yeah.
It's interesting is the word I like to say more than bad.
So I think the lesson there is that you probably want to try it in multiple places and make sure there's not some sensitivities to these little details that we might be missing.
Yeah.
And that was also the goal, as in the early discussions of this tool, who was going to be using it and how do we use it, is making the computations and the definitions of these transects easy enough for the user to be able to run more than one case. And that's really where this is. So always test the robustness of your data. And we're trying to make this as easy and consistent as possible for the user.
Excellent. I think, approaching that with a critical eye still, and not just looking at the straight output, right? You need to bring that critical eye to that, because we have found, some issues with the topographic data set in some locations. So just be aware of those kind of issues. I did have a question about the high resolution areas. So when you're actually dropping a pin at that location and getting data, is it averaging, or are you just taking that cell value at that pin location? Can you explain that?
I think I'm interpolating. I don't know what we came down to in the end, whether we're interpolating between the 4 points, the 4 nearest point to it. I think I'm doing a 2D interpolation, or we take the value that is closest. I had done both. So
my memory is 2D interpolation.
Yeah.
Yeah, the way it was in MATLAB, it was a simple 2D bilinear interpolation.
Yeah.
Okay. And then that's what we did.
Excellent. Thanks.
I wanted to show the unofficial, undocumented feature here, that you can take your site and move it elsewhere, but you got to click on it to confirm it. And if it says yes, make sure that the coordinates up here get updated, okay? And it's gonna mess up, the results, so you would have to start over. So this is why it's not as perfectly robust. I always recommend starting over, but it's a nice way of just kind of playing around with your site. So I might just cut this off of the recording of this video. This works well, not when you're doing the energy grid line, but when you're in the database lookup, then it's easy because you're not messing with your grid lines or anything. And so it's just a nice way of getting your database data out. Any other questions? Otherwise, we can call it a day. And thank everybody. Please, as I've said, use this portal, test it, but also just give us the feedback of what you see the value, recommendations, and if there's some inconsistencies that you find. And with that, thank you.
Very good. Thank you, Sylvia.
Yes, thank you.
Thank you.
Thanks, everybody.
Bye.
Thank you.
Thank you.